When installing footer rebar and anchoring J-bolts for building steel, a question arises regarding grounding both elements. If the J-bolts are tied to the footer rebar, does bonding to one suffice, or are separate conductors required for each? While connecting to either the J-bolts or the rebar might seem inadequate due to their connection, it's generally recommended to bond to both for a more reliable and robust electrical connection. There are multiple reasons for this recommendation. Firstly, redundancy is achieved. Bonding to both the J-bolts and the rebar provides a backup in case one connection fails. This is crucial for maintaining a consistent and dependable electrical path to the building steel. The connection between the J-bolts and the rebar may not always be perfect or remain so over time due to corrosion, loosening, or other factors. Bonding to both components creates an alternative path for ground fault current, ensuring the building steel remains properly grounded even if one connection degrades. Secondly, code compliance often dictates this practice. Many building codes mandate that both the J-bolts and the rebar be bonded to the grounding system. These codes are designed to ensure a high level of safety and electrical integrity within the building. Checking your local electrical codes and regulations to determine the specific requirements for your area is important. Compliance with these codes not only ensures safety but also avoids potential legal and financial repercussions. Thirdly, safety is paramount. Bonding to both the J-bolts and the rebar contributes to the overall safety of the building by ensuring the building steel is adequately grounded. Proper grounding minimizes the risk of electrical shock and helps to protect equipment from damage due to ground faults or lightning strikes. By providing multiple paths to ground, the likelihood of dangerous voltage build-up on the building steel is reduced. In summary, although bonding to only one component might seem sufficient when the J-bolts are tied to the rebar, best practice dictates bonding to both. This approach enhances redundancy, ensures code compliance, and improves safety. It is crucial to consult with local electrical codes and qualified electricians to determine the specific requirements for your project. Consider the potential long-term effects of environmental factors on the connections between the J-bolts and rebar. Corrosion, vibration, and physical stress can all degrade these connections over time, potentially compromising the effectiveness of a single bonding point. Bonding to both components mitigates this risk by providing a more resilient and durable grounding system. Here are additional considerations when implementing this practice. Firstly, the size of the grounding conductors used to bond the J-bolts and rebar must be appropriate for the anticipated fault current. Refer to the National Electrical Code, specifically Table 250.122, to determine the correct conductor size based on the size of the overcurrent protective device in the circuit. Secondly, the grounding conductors must be securely connected to both the J-bolts and the rebar using approved methods. This may involve using listed grounding clamps, exothermic welding, or other suitable connection techniques. Ensure that the connections are mechanically sound and resistant to corrosion. Thirdly, consider the material compatibility of the grounding conductors and the J-bolts and rebar. Using dissimilar metals can lead to galvanic corrosion, which can weaken the connections over time. Select grounding conductors and connectors that are compatible with the materials being bonded. Fourthly, inspect the grounding connections regularly to ensure they remain in good condition. Look for signs of corrosion, loosening, or physical damage. Any issue should be addressed promptly to maintain the integrity of the grounding system. Fifthly, document the grounding system thoroughly. Keep records of the grounding conductor sizes, connection methods, and inspection results. This documentation can be helpful for future maintenance and troubleshooting. Sixthly, consider using supplemental grounding electrodes in addition to bonding the J-bolts and rebar. Grounding electrodes, such as ground rods or ground plates, can provide an additional path to ground and further enhance the safety and reliability of the grounding system. The National Electrical Code provides detailed requirements for the installation of grounding electrodes. Seventhly, ensure that all grounding connections are accessible for inspection and maintenance. Avoid burying or concealing grounding connections in a way that would make them difficult to access. Eighthly, consult with a qualified electrical engineer to design a grounding system that is appropriate for the specific building and its intended use. A qualified engineer can assess the potential risks and develop a grounding system that meets all applicable codes and standards. Ninthly, remember that the grounding system is only one part of a comprehensive electrical safety plan. Other important elements include proper wiring, overcurrent protection, and ground fault circuit interrupters. Tenthly, consider the impact of future modifications or additions to the building on the grounding system. Any changes to the electrical system should be carefully evaluated to ensure that the grounding system remains adequate. When bonding J-bolts and rebar, the goal is to create a low impedance path for fault current to flow back to the source. This low impedance path helps to quickly trip the overcurrent protective device, such as a circuit breaker or fuse, in the event of a ground fault. High impedance ground fault can create a dangerous voltage in the building steel, which could pose a shock hazard to anyone who comes into contact with it. Therefore, it is essential to ensure that the grounding connections are properly made and maintained. Here is some additional information about grounding electrodes. Grounding electrodes are typically made of copper or galvanized steel and are driven into the ground to provide a direct connection to earth. The National Electrical Code specifies the minimum size and type of grounding electrodes that are required for different types of buildings. The most common types of grounding electrodes are ground rods, ground plates, and concrete encased electrodes. Ground rods are typically 8 feet long and 1/2 inch in diameter and are driven vertically into the ground. Ground plates are typically 2 feet square and are buried horizontally in the ground. Concrete encased electrodes, also known as grounds, are made by encasing a length of bare copper conductor in concrete. Grounds are typically used in new construction and provide a very effective grounding path. When selecting a location for grounding electrodes, consider the soil conditions. The soil should be conductive and free of rocks or other obstructions. The grounding electrodes should also be located away from any underground utilities. The resistance of the grounding electrode to ground should be measured to ensure that it meets the requirements of the National Electrical Code. The National Electrical Code requires that the resistance to ground of a single grounding electrode not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional grounding electrode must be installed. When connecting the grounding electrode to the grounding system, use a listed grounding clamp or connector. The connection should be mechanically sound and resistant to corrosion. The grounding conductor should be protected from physical damage. In summary, bonding both the J-bolts and the rebar provides a robust and reliable grounding system for the building seal. This approach enhances safety, ensures code compliance, and minimizes the risk of electrical shock and equipment damage. Remember to consult with qualified professionals and adhere to all applicable codes and standards when designing and installing the grounding system. The National Electrical Code Article 250 provides comprehensive requirements for grounding and bonding. Familiarize yourself with this article to ensure that your grounding system meets all applicable requirements. Also, consider using exothermic welding to connect the grounding conductors to the J-bolts and rebar. Exothermic welding, also known as welding, creates a permanent molecular bond between the conductors, resulting in a very low resistance connection. This type of connection is highly resistant to corrosion and vibration and is often used in critical grounding applications. When performing exothermic welding, follow the manufacturer's instructions carefully. Wear appropriate personal protective equipment, including safety glasses, gloves, and a face shield. Ensure that the area is well ventilated. Here is some additional information about ground fault circuit interrupters or GFCIs. GFCIs are devices that are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing in the circuit and quickly interrupting the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. When installing GFCIs, follow the manufacturer's instructions carefully. Test the GFCIs regularly to ensure that they are working properly. In addition to GFCIs, surge protected devices or SPD can also help to protect electrical equipment from damage. SPD are devices that are designed to protect against voltage surges such as those caused by lightning strikes or power grid fluctuations. SPD work by diverting the surge current away from the protected equipment. SPD are available in a variety of types and sizes. When selecting an SPD, consider the voltage and current rating of the protected equipment. Also, consider the location of the equipment and the potential for exposure to voltage surges. In addition to grounding and bonding, proper wiring practices are also essential for electrical safety. All wiring should be installed in accordance with the National Electrical Code. Use the correct size and type of wire for the application. Make sure that all connections are tight and secure. Protect wiring from physical damage. Here is some additional information about electrical safety. Electricity can be dangerous if not handled properly. Always follow safety precautions when working with electricity. Turn off the power before working on any electrical equipment. Use insulated tools. Wear appropriate personal protective equipment, including safety glasses and gloves. Never work on electrical equipment in wet conditions. If you are not comfortable working with electricity, hire a qualified electrician. In conclusion, by bonding both the J-bolts and the rebar, installing grounding electrodes, using GFCIs and SPD, and following proper wiring practices, you can create a safe and reliable electrical system. Always consult with qualified professionals and adhere to all applicable codes and standards. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Consulting with a licensed electrical engineer or a certified master electrician will provide tailored solutions specific to the project's unique requirements, local codes, and environmental factors, ensuring compliance and optimal safety. Factors like soil resistivity, building size and type, occupancy, and the presence of sensitive electronic equipment may necessitate more elaborate grounding and bonding strategies. For example, in areas with high lightning activity, a comprehensive lightning protection system might be required, which includes air terminals, DAN conductors, and a dedicated grounding network. Similarly, buildings housing sensitive electronic equipment, such as hospitals or data centers, may require specialized grounding techniques to minimize electromagnetic interference and ensure the reliable operation of the equipment. In such cases, relying solely on the general recommendations might not suffice, and a detailed engineering analysis is crucial. Also, be aware that the National Electrical Code is updated every 3 years, and local codes may have additional requirements or amendments. Staying up to date with the latest code revisions is essential for ensuring compliance and maintaining a safe electrical system. Participating in continuing education courses and seminars can help you stay informed about the latest changes and best practices. Remember, electrical safety is not a one-time task but an ongoing process. Regular inspections, testing, and maintenance are crucial for identifying and addressing potential problems before they become hazardous. Develop a comprehensive electrical safety program that includes periodic inspections of grounding and bonding connections, testing of GFCIs and SPD, and training for personnel who work with electrical equipment. This proactive approach will help to ensure the long-term safety and reliability of the electrical system. Furthermore, consider the environmental impact of the grounding and bonding system. Using sustainable materials and practices can help to reduce the environmental footprint of the project. For example, using recycled copper for grounding conductors and minimizing the use of chemical grounding enhancement products can contribute to a more sustainable electrical system. In summary, while bonding both J-bolts and rebar is a good starting point, a comprehensive approach to electrical safety requires careful consideration of various factors, including local codes, environmental conditions, equipment sensitivity, and sustainability. Consulting with qualified professionals, staying up to date with the latest code revisions, and implementing a proactive maintenance program are essential for ensuring a safe and reliable electrical system.